So it's time. I'll just get going then. So, good evening, friends, or good morning, good afternoon, depending on where you are. So, welcome back after the summer break. It's a pleasure to restart the OSMU lectures. And our speaker today is Kaustubh Agashe from the University of Maryland. It's my pleasure to introduce him. He'll talk about is the Higgs composite particle. Kaustubh is a professor in the Department of Physics at the University of Maryland, and he obtained his PhD at UC Berkeley in 1998. And after conducting postdoctoral research at University of Oregon, Johns Hopkins University, and briefly at the Institute of Advanced Study in Princeton, he joined the faculty of the physics department at Syracuse University in 2005. He then moved to the University of Maryland in 2007. Kaustubh's research is in the field of theoretical particle physics. He works on ideas going beyond the standard model of particle physics, and this research includes building new models and making predictions for them which can be tested in experiments, and plotting direct production of new particles at high energy colliders and calculating their indirect detection in lower energy experiments. Kaustubh is a world expert on a composite Higgs sector using models of curved extra dimensions and extending such models to explain quark masses, including their hierarchy. He has also investigated excited states in such models, which result in a tower of particles such as heavy gravitons and more massive bosons and fermions. So we are looking forward to hearing from Kaustubh on this very important topic of is the Higgs boson a composite? Over to you, and pleasure to have you with us today.
Okay, thank you very much for the very nice introduction. And thank you also for the invitation to give this talk. So as I was telling the organizers, I'm planning to pitch this talk at the level of sort of a typical physics department colloquium. Um, Having said that, yeah, feel free to ask questions during the talk. Um, and obviously, after the talk, we will have also an extended Q&A session. Um, I would like to, again, discuss this idea that the standard model Higgs boson is composite. So just to give you a preview, um, so again, this composite Higgs idea, sorry, um, sorry about that. Composite Higgs idea is actually associated with the top quark also being composite. And so that's why the framework is called composite Higgs and top. And we'll see that this framework, again, very attractive because it can address many of the open questions of the standard model of particle physics. So a few of them are highlighted here. So one of them is the so-called Planck-weak hierarchy problem, or often called the hierarchy problem, which is just saying why is the gravitational force so much weaker than all the other forces of the standard model. Then there is another hierarchy between the masses of the various quarks and leptons, the matter particles of the standard model. For example, the up quark is much lighter than the top quark. Another idea which is interesting is that could the three forces of the standard model, could they unify, so-called grand unification or a grand unified theory or a gut? Then, of course, there is the puzzle of what forms the dark matter of the universe. So I'd like to show that this framework can actually have implications for all of these questions. But perhaps more importantly, there is a whole range of experiments which can actually test all of these implications here. Okay, so I think most of you are familiar with the standard model of particle physics. But anyway, just to set the stage and make sure everybody's on the same page, let me just give you a really, really lightning review. So, so again, the basic picture of the standard model is shown here. Feynman diagram: matter particles interact by exchanging spin 1 gauge bosons or force carriers. And there are three carriers corresponding to the three forces of the standard model. There is the electromagnetic force, there is a weak nuclear force, and there's a strong nuclear force. And the carriers are gluon, photon, and the W and Z. The matter particles are spin half or fermions. They come in sort of two types, quarks and leptons. Quarks have strong interactions, leptons don't. And each of these categories, quarks and leptons, comes in three generations or flavors, which get progressively heavier. Okay, so here's the up and the down quark, charm and the strange in the second generation, top and bottom in the third generation. So the top quark is the heaviest quark, actually the heaviest particle of the standard model, and the up quark is the lightest quark. Okay, then of course the last ingredient, but not the least, is the Higgs field or the Higgs boson. So this is a cartoon of the Higgs mechanism. Let me not go into details, but just to say that the idea is that the electromagnetic and the weak nuclear force is actually unified into this electroweak interaction or electroweak force or electroweak symmetry. But that symmetry is broken in the sense that the W and the Z gauge bosons, they acquire a mass by coupling to this Higgs condensate, whereas the photon remains massless. So therefore, the electromagnetic force is long range, whereas the weak nuclear force is short range. Okay, and again, this is similar to what happens in a superconductor, where the photon effectively acquires a mass by coupling to the condensate of Cooper pairs. Right. Okay, so again, just to set the scales. Oops. The mass of the W and the Z is given by sort of the size of the condensate times the coupling. We've measured the masses of the W and Z gauge bosons. We know their couplings, and so you conclude that the rough scale of the Higgs condensate is about 100 times the proton mass. Okay, just like the W and the Z get a mass. So again, most of you know the fermions in the standard model also acquire a mass by coupling to the same Higgs condensate. So the idea is that the top quark has a large coupling to the Higgs condensate. That's why it's very heavy, whereas the up quark has a very, very small coupling. That's why it's light. So again, roughly this 100 GeV or the weak scale is the mass scale of the heaviest standard model particles, the W and the Z, actually the Higgs boson itself, and the top quark. Okay, and just to say that the reach of the current colliders, namely the LHC, is sort of several TeV. That's about 1000 GeV, so that's about 10 times the weak scale, right? Okay, so let me then talk about the hierarchy problem. Again, I'm going to be schematic here. So the central issue is that there is a hint for much higher scales than the weak scale. So one such hint, sorry, comes from basically gravity or quantum gravity. Sorry, I'm still getting used to using the pointer. So again, that's the scale where gravity becomes strong, or quantum gravity effects become important. And that again is the celebrated Planck scale. That's 17 orders of magnitude bigger than the weak scale here. And the problem is that the Higgs condensate, being a spin 0 or a scalar, basically is, again, roughly speaking, dragged all the way up to the Planck scale because of just quantum field theoretic effects. Okay, so that means this hierarchy is very unstable in the standard model. Okay, right. So the solution to the hierarchy problem in general consists of again typically adding new particles at the TeV scale. So I call that new physics or new particles, or NP for short. And the idea is that, of course, random new particles are not going to do the job. So you need specific new particles here so that the quantum effects are screened, and therefore the Higgs mass or the Higgs condensate, is actually not dragged all the way up to the Planck scale, but instead it is only taken up to the 1 TeV, which is the scale of new physics, and then the weak scale being 100 GeV can be natural, right? Okay, so so I'll begin my talk, or the main part of the talk, by showing you, maybe it's sort of obvious, how the Higgs being composite at the TeV scale will address this hierarchy problem between the Planck and the weak scale. And I'll motivate that requires the top quark to be also composite. So of course, these are composites of some new strong dynamics, and that strong dynamics can be non-perturbative, and so it's a challenge to actually calculate observables in such a theory. So the very remarkable solution to this issue is that theories with strong dynamics can be dual to theories in extra dimension, in particular curved or a warped extra dimension, the so-called ADS-CFT duality. So the idea that we have followed is we try to model this compositeness of the Higgs and the top quark by going to the extra dimensional picture. Okay. So I'll roughly indicate that, but I may not have time to really go into details. What I really want to focus on is the signals from this framework. There are various kinds. There's direct production of the new particles at the roughly TeV scale. And again, when I say TeV, I'm really being rough. It might be 3 TeV, it might be 10 TeV. Then I'll talk about some indirect or low energy effects. And hopefully I'll have time to talk about what happens to the possibility of grand unification of the three forces within this framework of composite Higgs and top. And I'll try to indicate that in such grand unified theories with this composite Higgs and top, you nicely get or automatically get a dark matter candidate, which in turn leads to various types of signals. Right? And one general theme I want to develop here is that the techniques developed for studying the composite Higgs and top signals, they could have a broader or a more general applicability, right? Okay, so let's start with the idea that the Higgs is composite, right? So again, rough picture is that the Higgs boson is like the pion of a real QCD. So it's some bound state of some new constituents, maybe new quarks. But the compositeness scale is more like TeV as opposed to the GeV or a few hundred MeV scale for the pion and the proton. Okay. So of course, then it's almost a one-liner as to why we can address the Planck weak hierarchy problem. The reason simply is that as you go to energies above the TeV scale, the Higgs is no longer a point particle, and that prevents the Higgs condensate or the Higgs mass from being dragged up to the Planck scale. Again, very similarly to the pion mass, any quantum effects contributing to that being cut off by the QCD scale, or if you wish, the rho meson mass, which is about a GeV. Okay. All right. So as I already advertised earlier, composite Higgs also motivates the top quark being composite. And again, the reason is hopefully obvious from what I said, that the top quark is the heaviest fermion of the Standard Model. So that means it has a large coupling to the Higgs boson, but now I'm imagining that the Higgs boson is composite. And so then for the top quark to have a large coupling to a composite Higgs boson, it better be that the top quark itself is composite, okay? Because again, the coupling is largest among three composite particles, right? Whereas a coupling between an elementary particle and a composite particle would be very small. Okay,
Sorry,
and an
Kaustubh,
idea.
could I ask you a question?
Sure, sure.
Yeah, so is this like a theorem that a composite Higgs implies a composite quark, or
Um,
can you get away with having a composite Higgs without having a composite quark, top quark?
yeah, I won't say it's a theorem, but uh, very likely or motivated. Just because, again, just think again, QCD, pion is a composite and electron is elementary, right? So
Hmm.
the that coupling is small, again, simply because the electron is elementary, right?
Yes.
So yeah, that's the idea.
Okay, thank you, thank you.
Okay. All right. So again, the top quark, you can think of it as in quotes, a baryon made of, let's say, 3 quarks, because of course you want it to be a fermion, a composite fermion. Okay. Um, all right. In the same vein, actually, the idea is that the other standard model fermions are also partially composite. Okay. Um, so again, top quark is the extreme that it's fully composite, right? And so here's the rough picture that the standard model fermions, they have a component which is elementary and a component which is composite. And it's rough analogy to what happens again in real QCD, whereas the photon um, actually mixes with the rho meson. Again, the photon starts out being elementary, but we know that there is a mixing with the rho meson. Okay, so of course that is for spin 1 particles. Here we are saying that something similar could happen with spin half particles. Okay, and so the idea is this degree of compositeness, the sine theta here, can vary over a wide range, and it's natural for that to happen. Let me not go into details. So the idea would be the sine theta is large, basically 1 for the top quark, but the sine theta is small for the up quark. And again, that can happen readily. And so if the sine theta is small for the up quark, the composite component is small, but the Higgs is composite. And so then it's clear that when this guy couples to the Higgs, which is composite, you got to go through this small component here for the up quark, and that explains why the up quark is so much lighter. Okay, so in this sense, the flavor hierarchy can also be addressed. Um, as I said in the outline, this idea is rather old. Actually, by now, I guess 20 years old, sorry, 40 years old, I say it. Okay. But again, if I try to write down purely 4D theories, you run into difficulties with trying to compute. Again, similar to the difficulty we face with real QCD. But then there's this remarkable duality, ADS-CFT, which says that I could have a dual description, which could be more readily tractable or weakly coupled, but that involves an extra dimension, which is, again, warped. And that's this Randall-Sundrum model, basically. Okay, and so we can construct realistic models of composite Higgs, but now in 5 dimensions. Okay, so that's the idea. Okay, now I don't really have time to go into too much details of this extra dimension description, so let me just outline the sort of the main idea. Um, Roughly, the intuition behind this duality, again, very schematic, is that in the purely 4D theory with strong dynamics, you of course expect a tower of bound states. Okay, just like what you get in QCD. There is the rho meson, but then there is the heavier excitations. Okay, and you can show that if I instead go to a 5-dimensional theory, so a field sort of living or propagating in the bulk, as we call it, or in the extra dimension, then from a 4-dimensional viewpoint, that field, extra dimensional field, appears actually as a tower of particles, which is called a Kaluza-Klein tower. Okay, and the simplest way to see that is this is like the modes of just a particle in a 1-dimensional box, just solving Schrodinger's equation. Okay, so this extra dimensional idea or description, I think deserves maybe a separate colloquium, and that's what I'm trying to indicate at the very bottom. That indeed I had given a colloquium from an extra dimensional viewpoint earlier, right? But here again, since I don't have enough time, let me just give you a snapshot of how things look like in the extra dimension. So remember, in the 4D picture with the composite Higgs and strong dynamics, I said that there is a varying degree of compositeness. So the up quark is less composite or very less composite, and the top quark is almost fully composite. Okay, so the idea is that that varying degree of compositeness we can sort of geometrize by using what are called profiles of these standard model fermions in the extra dimension. Okay, so here's this extra dimension, which is compact. Here are the two endpoints of the extra dimension. They are often called the UV and the Planck brane, or the Planck brane, and the IR or the TeV brane. Okay, so the idea is that Higgs being composite says that it is localized on this end, the infrared end, but the up quark being mostly elementary says that it is mostly localized near the other brane. Okay, and so this up quark has a small profile on the Higgs brane, and that small profile of the up quark on the Higgs brane says that the coupling of the up quark to the Higgs is small. Obviously, then the top quark, that's this red line here, is highly peaked near the IR brane, the same brane as the Higgs. That in the 4D theory is just saying that the top quark is almost fully composite. Okay, and similarly, the 4D graviton, you can argue that it's going to be localized near the UV brane, and the Higgs being localized here, that is central to solving the Planck-Weak hierarchy problem. Okay, all right. So again, as I indicated earlier, the explicit calculation will be done in this 5-dimensional model, but here I'm going to continue to use sort of a more 4D picture with composite Higgs and so on, just to summarize the signal. Okay, so it's going to be a rather qualitative, but hopefully that's good enough for this talk. Okay, all right. So so again, I really want to focus on how are we going to test this possibility. Okay, so these new signals are of course going to come from the new particles in this game, which are the heavier composite with a mass of TeV. Again, TeV could be 3 TeV, 5 TeV, maybe even 10 TeV. Okay, so to know what those signals are, I'd better first find out who are these new composites, what are their quantum numbers, and so on, and what are the sizes of their couplings. Okay, so let's do that, and let's do it again using the 4D intuition with strong dynamics. We're already familiar with one example of such strong dynamics, namely the QCD and the hadrons. Okay, right? Okay, so so here's kind of my analogy with QCD. So this side is the composite Higgs, that side is a real QCD. So in the framework at hand, I'm saying that the Higgs and the top, they are composite. Of course, Higgs has electroweak charge. Top quark also has QCD color charge. Okay, so that's the analogy is Higgs is like a pion made of quarks, but of course, pion has electric charge. Okay, so on this side, the QCD side, the fact that the pion has electric charge says that the quarks, the constituents of the pion themselves have electric charge. So that means there is a quark current which is coupled to the photon. Okay, that's just the gauging of the U1 or electromagnetism symmetry of QCD. Okay, so then going over to the composite side, composite Higgs side, that says that the constituents here, you might want to call them technique quarks. Okay, they should also carry even QCD color and electroweak charges. Okay, so that means that the elementary standard model gauge bosons, including the gluon, the WZ, and the photon, they are going to couple to those technique quarks. Okay, right? Again, going back to the QCD side, this quark current to which the photon couples, it can interpolate spin 1 massive hadrons, the rho mesons. You might call it heavy photon when it acts on the vacuum. Okay, right, and again that's sort of indicated here. So again, then going back to the composite Higgs side, this current here made of the techniquarks or the constituents, okay, is going to excite composite massive gauge bosons. Again, you can call them heavy WZ, gluon, and photon. In the 5D language, they would be the Kaluza-Klein, gluon, photon, and WZ. Okay, and again, that's indicated here. Okay, so again, you can see kind of the analogy between composite Higgs and real QCD, right? Okay, so and then extending this analogy to the couplings. Again, the slide is a bit busy, right? So let's start here. The largest coupling is between three composites. Okay, let me restrict here to just three composite. There are also four composite couplings. Okay, and for example, in real QCD, that's the rho pi coupling, for example. Okay, so same thing is going to happen in the composite Higgs. So that means these composite gauge bosons, composite gluons, photons, and so on, they are the analogs of the rho. They are going to most strongly couple to top and Higgs. Why? Because the top Higgs are also composite. Okay, so that's the largest coupling. Okay, and obviously the smallest coupling is, as I already indicated, where I have elementary fermions or particles coupled to composite, and the QCD analogy is, of course, rho coupling to E plus E minus. Rho is composite, electrons are elementary. And so here in the composite Higgs framework, the analogy is that the composite gauge bosons, again, that's similar to the rho meson, they are going to have a weaker coupling to the lighter quarks and leptons. Why? Because those guys are mostly elementary, right? So that's the sort of the smallest coupling between one composite and two elementary particles of the standard model. When I say elementary, I mean approximately elementary. That includes up quark, electron, and so on, right? And then there's a category in the middle, which is sort of two composites and one, in quotes, elementary. That would be like the rho to pi gamma. Rho and pi are composite, photon is elementary. But let me not go into details of this topic here. I was mentioning it or writing it here because there's been some relatively recent work looking at signals from this category. All right. Okay, so bottom line here is largest coupling is composite gluons, WZs coupling to tops and Higgses. Smallest coupling is composite gluon photon coupling to electrons and up quark and down quark. Okay, all right. So with that in mind, we can start looking at directly producing these heavy composite spin one gauge bosons at the LHC or future energy colliders. Who are operating at energies much above TeV, right? Okay, so I'm going to collide protons at the LHC. They are made of basically up quarks. So to produce this composite gluon or KK gluon, as an example, I've got to use the coupling of the up quarks. Okay, I know that is small, but there's no other option. Okay, but once the composite gluon is produced, it's going to mostly decay into top quarks. It could decay back into the up quarks, but that process is going to be very, very small. This is going to really dominate. Okay, right? And again, that's what I'm writing here. So there's a small coupling in the production, but the decay dominated by the larger coupling. Okay, so the signal is going to be I have these top anti-top resonances with the mass of the resonance being a few TeV, right? And that leads to a interesting phenomenon, okay, which again is of more general applicability, as I'll indicate in a moment, okay, which is that, if you wish, before the LHC, let's say when the top quark was discovered at the Tevatron, those top quarks were mostly produced at rest. Actually, even at the LHC, most of the top quark production is right above threshold. So when the top quarks are at rest, of course, we know that the top quark decays into a W and a B quark, then the W decays into two quarks or lepton and neutrino. Okay, but the point is, this guy's at rest. W is kind of heavy, so even W is basically at rest. And so you see that the decay products, the final quarks here and the bottom quark here, or the lepton here and the B quark here, they are very well separated. Okay, so it's a rather clean signal. Okay, but here, what's happening is the top quarks are produced by the decay of these composite gluons, whose mass, let's say, is 3 TeV. Okay, and so therefore the energy of each of the top quarks is 3 TeV divided by 2. That's about 1500 GeV. The mass of the top quark is about 150 GeV roughly. And so you see that these top quarks are boosted. Okay, so their gamma, the Lorentz boost factor, is something like 10, as opposed to being roughly 1 in the standard model production of top quark. Okay, so that means I take the process that I showed before, which is the W and the bottom quark emitted back to back, but I'm going to boost this whole system. And so now my W and the bottom are going to have a small angle denoted by this theta, roughly 0.1 in radians, and that's given by this 1 over the boost factor. Okay, and so it's clear that, so again, the W is going to decay into 2 quarks or a lepton, but those W decay products and the B, they're going to be almost right on top of each other. Okay, and so this is a challenge for the standard way of detecting top quarks, and that actually motivated coming up with these newer ways to identify the top quark. Okay, and again, here's this cartoon here. So first, I should say, of course, the quarks manifest in detectors as what are called jets, which is just a pair of hadrons. Okay, so on a coarse-grained level, you would really see just a top jet. Okay, as a kind of a single fat object. Okay, again, unlike the standard model production, where bottom quark and the W are well separated. Okay, so here the W and the B are merged, so it's really again a sort of a single fat jet. Okay, but then you can look deeper into that fat jet, an idea called jet substructure. Okay, in order to figure out that this fat object is really a top quark. It's not a standard QCD jet. It's not a single quark or a single gluon hadronizing. Okay, and this has led to a really tremendous effort joint between theorists, phenomenologists, and experimentalists. And so here's just one example of this search. Okay, so this blue shaded region is what is the upper limit. I should tell you what the axes are. That's the mass of that TT bar resonance on the x-axis. That's the cross-section limit. Okay, so you need to be living below here. Okay, to smaller cross-section. Okay, why? Because of course anything here, the cross-section is so large that the LHC should have seen an excess of these boosted top quarks, but they don't see it. Okay, so again, that's the experimental limit, and this dashed red line is what comes out of a 5-dimensional calculation for this cross section. And of course, then you see where the two or the blue line and the red intersect. That's about 3. So that's the upper, that's the lower bound on the composite gluon in this model. Okay, I should say that this is an old plot, so probably now the bound is more like 4 TeV. Okay, but again, just to say that this is in the boosted top quark regime, and so here's a picture of this an actual event, I think. Okay, right. Okay, so so I think, yeah, so this is one sort of fat jet made of these subjets, and here's the other one. Okay, right. So again, this was just to say, don't bother with the details, but just to say that real events with this boosted top quarks have been seen. But of course, this event likely is just a standard model background. Okay, there's no evidence for an excess of such boosted top quarks. Okay, but again, just to highlight that this idea of looking at boosted top quarks, and similarly you can do boosted Ws and Zs and Higgs bosons. Those could come from decays of composite Ws and gravitons and so on, right? And so this has really led to this sort of almost an industry of trying to detect boosted standard model heavy particles, WZs and Higgs, no matter whether they come from these composite gluons or from some other heavy resonance. Okay, and so that's what I mean by general applicability. Okay, in particular, I think it's still going on. There's an annual Boost conference since 2008, sort of dedicated to such signals. Okay, right. Okay, so that was one category of signals where I directly produce the heavy particles. The other possibility is that I'm at low energies, so I cannot directly produce those heavy particles, but I can look at their virtual effects or off-shell effects or indirect effects. And the rough idea is that I'm exchanging this new particle between standard model particles on the outside. You at energies much below the mass of this new particle, you get a short range or a suppressed force. Is very much like how the W exchange at low energies reduces to a 4 fermion interaction. Okay, so at low energies, you just end up getting this effective 4 standard model particle interaction. Okay, what I'll quickly try to show you is that such effects of these composite W's and Z's and so on can actually modify some of the properties of the standard model particles, in particular the Higgs and the top. Those are the guys who are most sensitive to these virtual effects. That's because those are the guys most strongly coupled to that heavy composite physics. Okay, and so the idea here is that you're working at low energies, so you're only producing standard model particles. You're not producing the heavy particle, but you're going to try to probe these modifications of the properties. Okay, and of course, the name of the game is a precision study. Okay, again, you're at low energies, so you can abundantly produce these standard model particles and study their properties. Okay, so of course, these kind of searches are complementary to the ones I showed before. Okay, so again, there are various types. So I probably might just talk about a sample of them. Right. So for example, the top quark coupling to the Z and the Higgs is shifted. Okay, so I'm calling it shift in the existing coupling. Okay, right. So, and again, that happens because of the exchange, or what is called integrating out these heavy compounds. Okay, and so this reduces to this. So I'm calling it a delta times a standard model coupling. Okay, right. So again, a TT bar Z couplings already exists, but I'm saying it's going to be modified. Okay. There can also be new couplings induced, which were basically negligible in the standard model. And one way to see that is the composite top coupling to the Z is shifted, but the charm quark is not composite basically, so its coupling is not shifted. And so, but we know that there is mixing among the different generation. You can argue that that generates a top charm Z coupling looking like this here. So the same delta that appeared before, but now multiplied by a mixing between the top and the charm. Okay, so this top charm Z coupling is extremely tiny in the standard model. So if you see an effect of a top charm Z coupling, it's likely evidence of this new physics. Okay. Okay. So again, this is a busy slide, so I won't maybe get into all the details. But just to say that there are various options. I could be at the LHC. I produce TT bar. Again, these are at low energies. Okay. Basically just standard model production. Okay. But now I can have a top quark decay into a charm and a Z or a Higgs using those new couplings. You can do something similar at E plus E minus colliders. And there's talk about such colliders in the near future, hopefully. So in fact, one example is at a collider with this energy, 250 GeV, where I cannot produce two top quarks, I can nonetheless produce a top and a charm using this new coupling here, so often called single top production. Okay. Of course, if I go to 350 GeV E plus E minus collider, I can produce two top quarks. Okay, and then do something similar to what I do at the LHC. Okay, so here are some numbers indicating what's the sensitivity of these future colliders and what are the levels of signal expected in this model. But again, let me not go into that. Okay, so another nice result I wanted to talk about is that we already saw that there are new contributions to top quark production at the LHC. The one I talked about was this resonant contribution here. Okay. Okay. So what I'm plotting here is the invariant mass of the TT bar pair. So this bump here is this composite gluon, but at the LHC, I can also sample the top TT bar invariant mass, which is smaller, which is, let's say, much below TeV. Okay. And the reason for that is, again, I'm colliding protons at 13 TeV center of mass energy, but the energy of the constituents actually varies. Okay. It can vary all the way from, well, up to 13 TeV to, much, much, much smaller. Okay. Right. And that's one of the nice features of the of Hadron Collider. Okay. And so earlier, again, I was talking about this, looking at the boosted top quarks, looking at, again, a bump. But there's also this effect, okay, which is, if you wish, off-shell Kaluza-Klein gluon. Okay, so again, that's the process. But if I go to energies much below the mass, it effectively looks like just QQ bar going into TT bar. Okay. So again, I'm here. Let's see what we can do with this. Okay. What I'm going to show you is that these TT bar pairs, which are not boosted, they are at much lower energies. They add to the standard model production, and they actually have an implication for measuring of the top quark mass itself. Okay. Okay. Now that seems a little bit counterintuitive at first sight, because you might say, okay, I've already measured the top quark mass, so why am I saying that there is an implication for that measurement? Okay. And the argument is that the existing methods, they are assuming that the top quarks are produced purely by standard model means. Okay. And so the idea is I'm going to make a prediction for some distribution as a function of top quark mass, and the standard model as the theory, match it to the data, and get the top quark mass. Okay. But now what I'm saying is that the theory has to be modified. Again, these are top quarks produced at low energies, but there is a contribution from these heavy composite gluons, which have been integrated out. Okay. And so if I change the theory, fit to the same data, I'm going to extract a slightly different value of the top quark. Okay. The bottom line here is we'd better have methods which can measure the top quark mass independent of the production mechanism. Again, existing methods don't quite do that because you need to supply some production mechanism. That's what I mean by theory here. Okay? And so we actually came up with an idea for a production model independent way of measuring the top quark mass. And again, this idea can be generalized to other heavy particles in the standard model or beyond. Okay. So I don't think I have time to really go into details. So maybe I will just summarize. I won't go into actual proofs and so on. Okay. Right. But just to back up a little bit, because again, maybe not all of the audience will be familiar with the idea of measurement of a heavy particle mass. So of course, you're going to measure it by looking at the decay products, often I call child particles. So here it is. Here's the parent. Here are the child particles. Okay. What I want to do is have a method which is independent of the production mechanism. Okay. Now, if all of the decay products are visible, then it's easy because all I do is take the 4 momentum of all of the visible decay products, square it. That's going to give me the mass of the parent. Okay. But if there are invisible particles among the decay products, then you cannot reconstruct the full 4 momentum of that parent particle. And so therefore you cannot get the mass in that way. Okay. Right. Also, the challenge is that this parent particle, again, is in general boosted in the lab frame, but that amount of boost, again, is unknown a priori. that depends on the production details. Okay, and so that makes it challenging to measure a heavy particle mass if there are invisible decay products. Okay, but what we realize is that using just the energy of the visible particles, we are able to actually measure the top quark mass independent of the production details. Okay. Now you might say, how can that be? Because energy is not Lorentz invariant, obviously. Okay. It depends on the boost of the parent particle, and again, that boost is varying event to event. Okay. Yet I'm trying to measure a mass, which of course is a Lorentz invariant quantity. Okay. So what we are able to show is that it is true that the shape of the energy distribution of this visible decay product, that again depends on the boosts of the parent particle, therefore depends on the production mechanism. But a feature of that distribution of the energy of the visible particle, namely the location of the maximum or the peak, that is actually unchanged, or it's invariant under the boost of the parent particle. Okay, so that's what we mean by this energy peak. Okay, right? Okay, so I had some more slides describing this, but let me not go into that. Let me just cut to the chase. Okay, so here's the formula for what we are proposing. I'm going to look at the top quark decaying into bottom quark, which materializes as a jet, and the W boson. I'm just going to look at the energy of the B jet. And the reason is the W can decay invisibly into a lepton and neutrino. So I look at the distribution of the energy of this B jet. And again, there is a distribution because this top quark has a distribution of boosts. Okay. But the location of the maximum in the distribution of the energy of the bottom quark, we showed that it is simply related to the top quark mass in this particular way. Again, largely independent of how the top quark is produced. Okay, so even the top quarks, which are produced from exchange of the heavy composite gluon, even they will have or those B jets will have a peak given here. Okay, and if we know the W mass, then and measure the location of the maximum, then I'm able to extract the top quark mass. Okay, and again, I had some plots to illustrate this, but let me cut to the chase to say that the CMS collaboration at the LHC actually has implemented our method, and so here's the plot from their paper. So those dots are the data points. On the x-axis, it's the energy of that B jet, and the location of the peak here actually will furnish information about the top quark mass. Okay, all right, and as I said, once we have developed the technique, kind of motivated by this composite top idea, obviously I can apply it to other cases. For example, there could be other new contributions to the top quark production, not just the composite gluon, but something else, maybe supersymmetry, right? Even in the presence of those other contributions, our method will be able to extract the correct value of the top quark mass. And obviously, I can extend it to other particles. Okay. All right. So I think I have, I guess, 15 minutes, maybe roughly, because we.
Yeah, you can take another 15 minutes. Sure.
Okay. Thank you. So, okay. All right. So let me then very quickly talk about this idea of gut or grand unified theory with this composite Higgs on top. But maybe before I go that, are there any questions? So again, some of my discussion was more phenomenological, but that's what attracts me quite a lot because there's a possibility to test these ideas.
Would you kindly summarize the top quark mass issue? The naive question from an outsider. So we know the top quark mass has been measured. It is within certain error bars. So what is the new thing that's happening now?
Yeah. So yeah, sorry, I kind of went quickly through that. Okay, so the point is that the existing methods assume that the top quarks are produced only by standard model processes.
Okay. Yes.
Right.
Mhm.
Right. But here I'm saying that there is a new contribution to the what's called the TT bar production
Mhm.
coming from integrating out the heavy composite gluon. Okay.
Okay.
Right. And so my theory here to be used in the prediction is now needs to be modified. Right.
Okay.
Um, and so when I
Mhm.
fit to the same data, that means with this new theory, I'm going to extract a different value of m top. Okay. That's the idea. Okay. So we want to have a theory agnostic way to
Mhm.
measure the top quark mass, and that's what we developed using the looking at the maximum of the energy of the B jet coming from the top quark TK.
So the current measurements of the top quark mass assume the standard model to be valid.
Exactly. Yeah. Yeah.
Okay.
So which may
Okay.
well
Thank you.
be the case. Maybe there's no new physics, but you don't know. There might be new physics, and of course the problem is we don't know. We don't know what that new physics is, right? I mean,
Yes.
so that's what I mean by have a method which doesn't rely on the theory input.
Okay. Thank you.
But,
Understood. Yes.
yeah. Okay. So
Can I
yeah.
do
Go
you
ahead,
have any
please.
feeling for why? Do you have any feeling for why nature would kind of favor certain fermions over other fermions? Like why is the top singled out so much as being composite versus other particles?
Um, yeah. So maybe I should answer the question in this way that we have these many fermions. Okay. So sorry, this goes back to my idea. Yeah. Okay. So okay. So again, the idea is there is a varying degree of compositeness, this sine theta, right? And it's actually I don't maybe I'll can explain this later. It's easy to get hierarchies here without putting in any hierarchies to begin with. Okay, and so the point is we are saying, let's say there are well, there are 6 quarks and 3 charged leptons. Okay, so if they have these 9 standard model fermions. Okay, so if you kind of roll the dice, then the sine theta, you'll get a distribution. Okay, there are some fermions will have small sine theta, others will have large, and others will have something in the middle. Okay,
Right. So
that's
what I'm asking then is why this particular distribution?
yeah. So we cannot address why exactly top quark is 175, the bottom quark is 4.5 GeV, and the electron is half an MeV, right? Those specific numbers we cannot explain. Okay, but what we are addressing is how can you get such big hierarchies in the standard model without putting in any hierarchies to begin with. Okay, and so that's done via this degree of composite. Okay.
Okay.
Um,
Okay.
so
Thank
so
you.
so again, I can explain later that it's easy to get this degree of compositeness to vary. Okay. So the idea is that it's easily possible. In fact, it's generic that then some fermions are heavy because of large sine theta, others are light because of small sine theta, and the particles which are heavy, you call them the top quark, right?
Well, okay, but there's particular charges associated with the top quark as well too. So
That's
there's
true.
kind of
So
there is a choice.
we're not able to explain why it's the top quark which is the heaviest and not the tau lepton. Okay.
Exactly. Yeah.
Yeah.
Okay.
So
All right.
I mean, yeah.
And you wouldn't have any sort of explanation as to why, like the top quark really is singled out with its mass, and that it's got a mass that's quite a bit larger than the other fermions. Would there be any? Do you see any reason as to why like the distribution should be such that one particle in particular is singled out so much?
Good point. Yeah. Actually, yeah. Unfortunately, the theory as it stands cannot really account for that. So you're right. I hear your point that based on what I said, some random distribution of these mixing angles sine theta, you might have said, oh, there is a top quark at 175, which is of course the weak scale basically, right? But you might have expected some particle in the middle, I don't know, 50 GeV, another one at 10 GeV, and another one at 1 GeV, and so on.
Right.
But we are instead, you're right, we are seeing sort of a gap that there is a top quark, then the next one is 5 GeV or 4 GeV for the bottom quark, right? Yeah, so I think now you might just say there are 9 fermions, so if you distribute them randomly, well, by chance, maybe, 8 of them are kind of bunched on the lower side. That could happen, relatively lower side, right? Right? You know what I'm saying. If you had 100 fermions, then I might have really expected a more uniform distribution.
Yeah. Okay. Yeah. Okay. Thank you very much.
Okay. All right. Okay. So, so again, I'll probably have to be brief here, but let me try. So I think most of you probably know of this idea of gut. Okay. The 3 forces have different strength at low energies, but there is a logarithmic evolution of them with the energy scale at which you measure them. And so you can hope that at high energies, maybe the 3 forces unify. Okay. And indeed, and that's shown in this plot here. So the x-axis is the evolution in energy on a log scale. The vertical axis is the sizes of the couplings, actually the inverse of the couplings. Okay. So if you extrapolate the standard model couplings, they sort of tend to meet, but of course the meeting is not really good. Okay. Now, in the case with the composite Higgs and the top quark, this what is called the evolution or running is modified, and for sort of 2 related reasons. One is that the top and the Higgs are composites, okay, above a TeV scale, and so clearly that is going to change the evolution. And basically, what you need to do is above TeV, you replace the top and the Higgs by the constituents who are strongly coupled. Okay, right. So again, let me make it short. So again, the dashed line is the standard model evolution, not meeting very well. But remarkably, we were able to show, or we found that kind of naturally, that with the composite top and the Higgs, the modifications, I'm calling them kinks, in the evolution starting at TeV, so that's TeV, okay, above which the compositeness comes in. The modifications are such that you actually can unify the couplings very precisely. Okay, so that makes the idea of granularification in this setup very attractive. Right. So again, I can get into more details later, but then I want to quickly say that the same idea of grand unified theory with composite top and Higgs also can furnish a candidate for the dark matter, and again, rather naturally. I guess I don't need to motivate the idea of weakly interacting massive particle or WIMP as a dark matter, right? So roughly, if the mass is weak scale, the annihilation rate is a weak scale strength, then you get the abundance in the right ballpark from the mechanism of so-called freeze out. Okay, the bottom line here is a WIMP is a good dark matter candidate. So we want to see if naturally our theory here could encompass such a WIMP. Okay, and it turns out the answer is yes. That and it's really a spin-off of trying to prevent the proton from decaying. Okay, so in many of these theories where you add new particles at the TeV scale, you worry that those new physics or particles could lead to the proton decaying. So often you have to impose a symmetry on the interactions of the new particles so that you suppress proton decay. Okay, so in this case, long story short, the symmetry imposed to suppress proton decay actually gives a stable particle, and the stable particle is the lightest gut partner of the top quark. Okay, and that gut partner could really be a WIMP. Okay, and that's what I'm trying to indicate here. Its mass could be a few hundred GeV. That it could be easily lighter than the typical composites, which might be at more like 3 TeV. Okay, so again, it's not enough just to have a mass at 100 GeV. It also needs to have the right interaction strength. And so again, let me skip details. But the idea is that this dark matter candidate, this exotic right-handed neutrino, which is the gut partner of the top quark, it does have the weak scale or weak strength interactions so that it can lead to a right abundance. And again, that's being shown in the plot here. Similarly, you can look at signals of this dark matter. Again, it's a WIMP, so there's a standard detection. And this plot shows you that, right? But let me just take a minute to say that so far I was talking about sort of standard signals, freeze out and so on, of this WIMP, something you're familiar with from, for example, supersymmetry, with the lightest supersymmetric particle being stable. By the way, that lightest supersymmetric particle being stable also is a spin-off of suppressing proton decay, imposing something called R parity. So in this case, composite Higgs, it's similar. That is, you try to suppress proton decay using a symmetry, and as a bonus, you can get this dark matter candidate. Okay, but what is new here, non-standard, is that the symmetry stabilizing the dark matter is not a parity or a Z2; it's a Z3 symmetry. Okay, and that leads to these new kind of interactions where I could have 3 dark matter particles shown in orange, or their partners. By partners, I mean heavier particles which are also charged under the dark matter stabilizing symmetry. Okay, so 3 of them can interact with a bunch of standard model particles. That's something which cannot happen in a case when the dark matter is stabilized by Z2, because Z2, you got to have 2 or 4 of the new particles, the orange particles, dark matter, and its cousins, and a bunch of standard model particles. Okay, and so this Z3 symmetry, this new interaction here, we showed that it could lead to interesting signals. For example, at colliders. Again, let me skip here, but let me take a minute just to mention that the Z3 symmetry can give rise to a very interesting idea called boosted dark matter. And the idea is that dark matter annihilation, right? And again, these are ambient dark matter. They are at rest, basically. Because of what I said, it can give rise to, let's say, 1 standard model particle in the final state and 1 dark matter. Okay. Again, it's an interaction between 3 of these orange particles that's characteristic of Z3. Okay. But then you see that this outgoing dark matter particle will be boosted. Okay. So the idea is ambient dark matter, which is at rest, basically its annihilation can give you a flux of boosted dark matter. Okay. Whereas, so of course you try to detect ambient dark matter, but that's basically at rest when it enters our detector. But now we are saying that there's a new component, if you wish, to ambient dark matter, which is this boosted, and you can try to detect that. Okay. And so we constructed a, again, inspired by this composite Higgs top, and the grand unified theory, and the dark matter candidate, we built a toy model of this boosted dark matter. Again, that is shown here. But let me just get to the bottom line, which is that such boosted dark matter can be detected at experiments which are called super Kamiokande, hyper Kamiokande, and so on. Okay, these experiments were designed to detect neutrinos, but they're also useful for detecting standard model particles coming from annihilation of dark matter. Okay, so again, just going back here. Here. So again, in the dark matter annihilation, you could also have standard model particles. And so far, these detectors were used to detect those standard model particles. But here we are saying that the same detectors can be used to actually detect the boosted dark matter. Okay. And so again, here's an example of motivated by composite Higgs and top, we discovered this general phenomenon of boosted dark matter. And that has general applicability because as I'm saying at the bottom, I could construct other dark matter models where there is a similar phenomenon, and you can look for those things. Okay, so at this last topic about a phase transition in the early universe associated with this composite Higgs, again at temperatures much above TeV, I'm going to deconfine the constituents of the composite Higgs. So there's going to be an analog of a quark gluon plasma, and then I cool down. And then at some point, I need a phase transition to get to the confined phase. Okay, so very much like the QCD phase transition, but now happening for the new strong dynamics. And so that has very interesting implications. Okay, so since I'm running out of time, let me summarize. Okay, so again, this is the same as the previous slide, right? So again, this framework of composite Higgs and top, addressing the puzzles shown in the black. So why is gravity weak? why is up quark lighter than the top quark? Same thing as on my whatever second slide. But now in green, I'm telling you how those solutions to the various problems, let's say, can be tested in various experiments. Okay, so that's the emphasis here. Okay, so again, the idea of solving the hierarchy problem, the manifestation is that I'm going to get TeV, few TeV, maybe 10 TeV, heavier composites. You could try to probe them at the LHC. They give boosted top quarks. So that's what we saw. Solution to the flavor hierarchy. I didn't have time to get into details, but that can lead to flavor violating signals. I think I mentioned one of them, which is the top quark decaying into charmed quark and Z. That's a change of flavor. Okay. The idea of grand unification of forces, which works very well, led to the possibility that there are other gut partners of the top quark other than the dark matter candidate. Those gut partners actually are charged under electroweak and color, and so you could produce them at the LHC. Then there was one gut partner of the top quark, neutral guy, which is the WIMP. That is a candidate for the dark matter of the universe, can be detected in a standard way at LZ, xenon, and those direct dark matter detections, the usual types. But then we showed that there's also a new signal coming from a boosted dark matter. Okay. All right, so that's it. So let me stop here. Sorry, I went over time. But...
No problem, no problem. Thanks so much, Kaustubh, for a very informative and interesting talk on an important subject, nature of the Higgs. The talk is open for questions, please. You could kindly use the raise hand feature if you would like to ask a question. Maybe I could just start off while others join. Kaustubh, are there generic arguments which strongly favor a composite Higgs? Or at the end of the day, we might learn from experiment that after all, it's a fundamental scalar?
I think so far there is, of course, no experimental evidence, right, that the Higgs could be composite. In fact, the properties of the Higgs are being tested at the LHC as we speak, and there's no indication that there is any deviation from standard model. Okay, whereas compositeness of the Higgs at the TeV or few TeV or 10 TeV scale will predict deviations in the properties of the Higgs. Okay, just like I argued about coupling of the top quark to the Z is shifted. Okay, so certainly on the experimental side, there's no hint. So the motivation really is that well, it's one possibility, right? Higgs could be elementary or composite. So you want to probe both ideas, right? Why not? So it's it's good to search for effects of Higgs compositeness. But of course, my real motivation would be that this idea of composite Higgs, as shown in the slide here, can actually solve many of the puzzles of the standard model. Okay, so that's of course a theoretical motivation.
Right? I totally agree. It's definitely very attractive. But is the LHC already probing the scale at which you predict compositeness to show up? Not yet.
Yeah. So again, this compositeness scale, it's a bit of a sliding scale, right? Because I was arguing that the compositeness should be at TeV because I wanted to address the Planck-Peak hierarchy problem without significant tuning, right? Right. But of course, if I make the scale 10 TeV, okay, what's going to happen is that so instead of TeV, if I make it 10 TeV, the Higgs mass is going to be dragged to the 10 TeV scale. But of course, I can always fine tune. I mean, I didn't go into details of that, but you guys probably know. I can always fine tune to get the right Higgs mass. Okay, but the degree of fine tuning gets worse as I raise the Higgs compositeness scale, right? So the ultimate is the Higgs compositeness scale is Planck scale, which means basically Higgs is elementary. Then of course there's a huge fine tuning price, right? So fine tuning prefers a lighter compositeness scale, TeV, ideally even below TeV. But of course, as you already said, there are bounds from the LHC which are going the other way. They're saying no, compositeness should be more than 1 TeV, right? Right. So, but in that sense, you see, it's a sliding scale. That 10 TeV compositeness scale is slightly worse in terms of fine tuning compared to 1 TeV compositeness scale. But the 10 TeV Higgs compositeness scale is way better than Higgs being elementary up to the Planck scale, right?
Okay. Okay. Yes, I agree. I agree.
So
Thank
that's
you.
the and of
I'm
course
more,
it's a really there's no hard and fast rule that where do you stop in terms of fine tuning, right?
Mhm.
There's no line in the sand saying that oh, if the tuning is worse than 0.01%, then you stop, right?
Mhm. Okay. Yeah, I have more questions, but I'll come back. Others have questions too. David, please go ahead.
Great. Okay, thank you very much for the talk. So a few years ago, I came across some models that I don't remember very well, but they were about the Higgs being a composite of right-handed neutrino states, which seem kind of quite economical in the sense that we expect there to be kind of right-handed neutrinos to account for left-handed neutrino oscillations and so on. I'm wondering if you're familiar with those models and compared with having new kind of quark, strong interacting quark states, whether those neutrino models account for similar problems like the hierarchy problem, or whether there's a strong preference for adding new particles like new types of quarks rather than using, say, right-handed.
Yeah, so I'm not actually familiar with the that particular model, but yeah. So I think one thing I might say is that so yeah. So on this slide, I was trying to argue that. So again, I was motivating that the top quark should be composite because it has a large coupling to the Higgs. Okay, so that requires the constituents to actually carry QCD color. Okay,
Right.
In the same way as the pion, charged pion, of course, having an electric charge says that the constituent quarks should have electric charge. Okay, so I think this idea of composite Higgs, I don't see how to realize that if the constituents of the Higgs are color singlets. Okay, and remember the compositeness of the top was key ingredient in sort of, if you wish, explaining why the top quark is heavy, right?
Right.
But of course, I think I probably I get the spirit of your question in the sense right-handed neutrinos maybe are needed anyway to get the seesaw mechanism and so on. So it sounds like a minimal idea. Okay.
I think he's trying to connect the mystery of the Higgs with the mystery of the neutrinos.
Right. Yeah. So, but our idea here was let's not be guided really by minimality. Let's be guided by what are the possibilities. So here we're just saying it's easily possible that there is some new strong dynamics. And of course, maybe many of you are familiar with this idea. It used to go by the name of Technicolor, where you really say that it's scaled up QCD. Okay, so we know QCD, the strong dynamics, produces composites. So that suggests that, well, there's a possibility that there's a strong dynamics with a heavier compositeness scale, which could be playing out at TeV, and which could give the Higgs as a composite, right? So that was the idea.
Okay. If I could have a sort of short follow-up. So if you take out the motivation of the weak gravity kind of hierarchy, how strong is the motivation for a composite Higgs if you take out that kind of that factor?
Right. So probably I think I again get the spirit of your question, because of course the Planck weak hierarchy, this one here,
right,
is being questioned, right? This idea of naturalness, right? So what I like is that there is the other hierarchy, which is of a different kind, which is the flavor hierarchy, why the up quark is much lighter than the top quark and so on. Okay. So again, that, if you wish, independent of Planck weak hierarchy, would motivate the Higgs being composite. Again, I'm not saying that's the only option to explain the flavor hierarchy, but certainly if the Higgs was composite, then I can actually try to address the Planck weak hierarchy. And again, the idea was to have the standard model fermions being partially composite. So that's what I was showing in the slide here. Okay, right, and this again happens because there are elementary fermions mixing with composite fermions, a little bit like photon mixing with a rho. Okay, and so this degree of mixing can easily vary over a wide range, and getting a little bit technical. And the reason is that the elementary fermions couple to some fermionic operators of the strong dynamics, and the mixing depends on what are called scaling dimensions of those operators. Okay, so with just small changes in the scaling dimensions of the operators with which the elementary fermions are mixing, you can easily get rather large hierarchies in this amount of mixing. Okay, and so that is a nice way to generate hierarchies in the fermion masses, or really it's the Yukawa couplings. Okay, and again, that relies on the fact that the Higgs is composite, and so the coupling of the standard model fermion to the Higgs has to go via this composite component, right?
Okay.
So yeah, so I would say flavor hierarchy is a
Does that work also for the leptonic sector as well as the quark sector?
yeah, it works even for the leptonic sector. Yeah.
Right, sure. Yeah, great.
Yeah,
Okay,
both the standard model quarks, leptons, they are mixing with their composite counterparts. Yeah. And again, I just really want to emphasize that naively you might say the hierarchy, just to repeat, that the hierarchy in the fermion masses, let's say between the electron or the up quark and the top quark, is a factor of about 1 million, right? So of course, in this equation, I'm just saying that that hierarchy is here, factor of 1 million between the, let's say, up quark and top quark, or the electron and the top quark. Okay, so from this viewpoint, you might say, what did I achieve? Because I'm just translating the hierarchy into hierarchy in the sine theta, the mixing angle, or the mixing. But what I was saying earlier is that it's easy to get hierarchies here by just small changes in more fundamental quantities, which again is the what are called the scaling dimensions of the operators with which the standard model fermions mix or couple. Okay, so again, if you wish, this elementary composite mixing in the fermion sector, it is a little bit like, take QCD, real world. There is a proton, which is positive charge, which is a bound state. Okay, but in fact, in grand unified theories, if you work it out, there is actually a coupling of the positron or the electron, okay, which is elementary, to the proton as a bound state. Okay, and that can arise in a grand unified theory. Okay, so that's what we are imagining, that the positron mixes with the proton. That doesn't happen in the standard model, but if you have a grand unified theory, such a mixing can be induced. Okay, but then the amount of mixing depends on the what's called the scaling dimension of the operator interpolating the proton and so on. Okay, right. So again, even in standard model, let's say extended by a gut, there is this notion of elementary composite fermion mixing. Of course, spin one mixing is well known, photon rho. So all we are saying here is, well, if there's spin one mixing elementary composite, why not have it in the fermion sector as well? And that can easily get hierarchies here, and therefore address the flavor hierarchy.
Okay, great. Yeah, so thank you very much. Thanks.
Thank you. One more question, Kaustubh. So accelerators like LHC or other future accelerators, can they look for testing the compositeness of the Higgs in a model independent way, or do they need predictions of a specific compositeness model, which they then confirm or rule out?
So many of the indirect effects that I talked about, right, so-called virtual effects, those can be sort of, let's say, parameterized in just a effective field theory, right?
Okay. Yes.
Right. So so if I want to directly produce the resonances, the composite gluon, then yes, their spectrum and so on might depend on the particular model and the details of their couplings. Okay. Even then, I would say generically we do expect these composite gluons based on what I said, that the constituents carry QCD color. Okay. But you're right.
What I was saying was, sorry to interrupt you. Suppose an experimentalist says, okay, let's have a so-called Higgs factory, make lots of Higgs. And now let's test, is the Higgs composite? He doesn't know any theory. what kind of experiment would he do then to check
Yeah.
for?
So, for example, so you mentioned Higgs, but I could talk about the top quark as well. So what will happen is that the Higgs coupling to the W and the Z will be modified. Okay, and the modification is depends on the scale of compositeness, right? So what people have been doing is parameterize those modifications of the properties of the Higgs and the top quark and the W and the Z, in some standard way, and then you look for those deviations. Okay. So of course the size of the deviation, it's a free parameter, right? But what I'm saying is, no matter what the details of the composite Higgs models, generically you will expect effects of this type that I'm showing, that the Higgs coupling to W is shifted, and that can be actually again parameterized in what is called standard model effective field theory.
Great, thank you. That sounds
These are
very
just basically it's just higher dimensional operators involving Higgs and tops and W, right?
These are generic changes that will take place. Yes.
Sorry?
These are generic modifications that will show up here.
Exactly. Yeah.
Okay. Yeah. So a related question is, I have been doing with my collaborators some work on unification, which suggests that the Higgs is a composite of all the standard model fermions to which it eventually gives masses. The Higgs is made up of the very fermions which arise with their masses. So do you see any serious difficulty if the leptons and quarks are all sitting, and even the neutrinos and three families of sterile neutrinos are all somehow, forming a condensate, and that is the Higgs?
I think I need to know maybe the details of the model, but naively I would have said, so even here, right, you might have said, why didn't I make the up quark or the electron also have a high degree of compositeness? Okay.
Yes.
Right. That sine theta that I was harping about. You might say, oh, maybe make it 1 for even the up quark. Of course, one reason is, well, if I made it 1, then I would expect the up quark to be heavy, because I would expect it to have a large coupling.
The issue is that in my work, the quarks and leptons are not composites, not even the top quark. That's where I'm a bit worried. Am I missing something?
But they are the constituents.
They're fundamental. The quarks and leptons are fundamental, but the Higgs is made of them.
Right, fine. But I think in that case, I would expect in the scale of compositeness is TeV, I think I would expect that there might be too large deviation in the properties of the electron and the up quark. Okay, because again, they are. So I think there's new physics. Let's say the compositeness scale is TeV, just to be complete. Then there is new physics at the TeV scale, but I understand that the electron and the up quark are not composite, but they're elementary. But I think it's clear that they have to be order 1 or strongly coupled to that new physics, right? Because otherwise, how can they be constituents of the
That's a very interesting point.
So then the problem is I will get higher dimensional operators for the electron and the up quark suppressed by TeV, okay? But that would lead to too large deviation in their properties, okay? Something which is probably highly constrained by the current data, okay? So the reason, so again, in the model that I was talking about, it's the Higgs and the top, their couplings to W and Z, which are modified. But what's happening is, of course, by now, even the Higgs properties, top quark properties are being precisely measured at the LHC, okay? But not as precisely as the properties of electrons and up quark and muon have been measured, right? So meaning if the Higgs and the top is composite at the TeV scale, or if you wish, there are dimension 6 operators suppressed by the TeV scale, modifying properties of the Higgs and the top, that still might be marginally allowed, because it's only relatively recently that we are measuring properties of the Higgs and the top precisely for obvious reasons, because those are the heaviest particles of the standard model. So we got to them the last, but the bottom quark or the tau lepton or electron, we have of course measured their properties, since ages, and we see that those agree very well with standard model. So the bottom line is any dimension 6 operators or these indirect effects suppressed by the TV scale, I think would be hard to be consistent with the data for the electrons. And,
Okay.
right. That's
Well, that's very interesting. Thank you.
so
Maybe I
here
thought-
again, it's so again, as I was saying, because of that sine theta, it is true that the electron is partially composite, right? Going back to what I was saying here, right? So electron has this composite component, but that is small precisely because the electron is light, or the up quark. Okay? But that small component is going to give rise to shift in the coupling of the electron, just like I talked about shift in the coupling of the top, right? Because any amount of compositeness would change the properties. But those changes are suppressed by the sine theta, the very factor which suppresses the electron mass. And so that tells you that the shift in the properties of the electron are going to be very small. Okay. Of course, you have to check numerically. They might be very small, but you might say, oh, but maybe electron properties are measured more precisely. So you got to play out that game. But roughly speaking, the electron compositeness is so small that any effects on the shift of its properties are non-zero, but they're basically so tiny that
I think what I'll do is I'll send you my works privately and ask for your feedback. So if you like, is what I'm doing being ruled out, or blah blah blah? Is there a way out?
Sure.
So thank you. We can go on. Ashutosh has a question. Go ahead, Ashutosh.
All right. Thanks a lot,
Oh, hi.
Kaustubh.
Hi,
Hi, how are you? All right. Just to follow up on the discussion you and Tejinder and others were just having, when you say the properties would be shifted relative to the standard model, there are many of the things you were mentioning are not predictions of the standard model, like the electron mass or muon mass, not predictions.
Right. But I was specifically talking about, for example, the top quark coupling to the Z or the Higgs, right? So
which are very poorly measured.
Right. So exactly. But this theory predicts a shift and a rather sizable shift, because again, the top quark is highly composite, right? But that goes back to what I was saying, that so you're right. The top coupling to Z is actually, I don't even know if there is any measurement, but yeah,
exactly.
But if there is, it right. So in fact, that's what allows this idea of composite top to survive, right? Because we predict large shifts, but they have not been measured right now, right? So it was more saying that this is more target for the future experiments that even the LHC, high luminosity LHC, and so on. As you produce more and more top quarks, eventually, I think you will measure the coupling of the top to the Z with some precision, and then you can try to probe these coupling, right? Or actually, in fact, yeah. So maybe the Higgs is a better example. The Higgs couplings to the W's and Z's, I think those are being actually probed already, or have been measured and probed, right?
At a 5% level or so right now.
Exactly. Yeah. So exactly. So the precision is sort of poor enough that it allows Higgs compositeness at the TeV or multi-TeV scale to still be safe. Okay. Right. But yeah, again, as those measurements get more precise, the compositeness scale is going to be pushed up, right, even more. So I guess the point here was that if you're looking for shift in the existing coupling, the target is the top and the Higgs coupling, let's say to W's and Z's and so on. Again, simply because top and the Higgs are the standard model particles which are most composite. So they feel the effects of that new physics the largest, right? But again, coincidentally, those properties of the top Higgs are the ones poorly measured. Again, it's all correlated. The reason is because they are heavy. Right?
Go ahead.
No, that's all I'm going to say.
Yeah. So, I was somehow thinking that, if the Higgs is made up of standard model fermion, that's like a minimal modification leading to compositeness. I'm not introducing any new particles, but I'm removing the Higgs scalar nature using standard model fermions plus maybe sterile neutrinos. But yeah, I don't know whether Ashutosh is saying that there's a way out for me or whether there's no way out. I'm a bit confused right now.
Well, let me rephrase your question in a blunt way. The field is talking about a Higgs factory.
Mhm.
Now, the Z-Higgs coupling is the only one that Higgs factory really pins down well. None of the
Mhm.
others are going to be better than 1%, I think. But the Z-Higgs coupling is anticipated to reach 0.1%.
Okay.
Everything else, maybe Higgs to charm is 1%. Most likely, it just confirms the Higgs mechanism. But if you want to really probe a BSM theory like compositeness, I think the 0.1% is the one measurement, the Z-Higgs coupling, which offers some hope of BSM. So
Okay.
can you say something about whether you would support a Higgs factory which gets to 0.1% on Z-Higgs? It doesn't really do, top to Higgs that well because the TT bar threshold is really difficult for a circular machine. And TT bar Higgs is really quite high mass. And so a circular machine doesn't reach 400 GeV center of mass or something like that. So if you forgot all that and said, this Z Higgs coupling at 0.1% is really worth it, what would you say?
Yeah, so good question. So
0.1%.
yeah, so that's certainly one example. Now, so that's why I had this bullet point here that actually so again one will have to run the numbers, but there is a top charm Z coupling, which is really a new coupling in the sense, well, in the standard model it's extremely tiny. Okay.
Right.
So actually it's interesting that can be, so it involves the top part, but it can be probed by single top production even at a what you're calling a Higgs factory, so let's say 250 GeV. Okay, so that's another example of something
Good.
which could be probed.
Right.
Yeah. So I agree that you cannot do the TT bar because for that you need to be, of course, above 350. But the other thing I will say is, and again, Ashutosh, you know more about this than me, that at least with the FCC EE, they're talking about various stages, right? I mean, I think they're even talking about going about TT bar threshold. But maybe that's, I don't know, maybe it is too optimistic, but certainly 250. But the other thing is, I think they're thinking of running that at the Z pole as well, right?
Of course.
So, yeah, so possibly if you measure the Z couplings super precisely, much more than LEP, then even that would be relevant, okay? Because again, these TV or multi-TV compositeness will actually, I mean, as you know, contribute to what are called electroweak precision tests, S parameter, and so on, and that will shift couplings of the Z even to muons and whatever electron relative to standard model prediction, right? So again, already there are current bounds from LEP. Okay, that puts the compositeness scale at whatever it is, 5 TeV or right. But you can see where I'm going. That if you can measure the Z couplings, therefore the put bounds on the S and T parameters, let's say a couple of orders of magnitude stronger at this FCC E on the Z pole, then that will actually also probe the compositeness scale, right?
It would be useful to have the numbers because the two things you just said, the Z Higgs at 0.1% versus extreme high precision on the Z pole, the experimental setup is vastly different potentially. You could end up concluding that while the 100-kilometer tunnel is way too expensive and politically difficult, maybe. A 90 GeV collider of extremely high luminosity is something you could optimize for at a very different cost.
So with a smaller tunnel, you mean?
The smaller tunnel, existing tunnel even, right?
Right.
Existing tunnel Higgs factory with just much better RF cavities and things like this is something you might be able to afford. And if you say that extreme high precision Z measurements are
Right.
just as good as Higgs measurements for what you're motivating here, that's a very useful statement. Experimentally, cost-wise, actually get things
sorry,
done.
are you saying that with the existing LHC tunnel, it's possible to go to the 250 GeV or?
Barely. I mean, it was tried, of course,
Because of
right?
course, Lab 2 went up to whatever, 210 or something.
Lab 2 tried and they petered out at 214 or something.
But with new technology, because of course the issue is the synchrotron, right? Radiation.
Maybe, could be, yes.
Yeah, I mean, I actually, yeah. So I haven't done the numbers here as to which option is better, the Z pole or the Higgs factory. I guess I had in mind. I mean, I thought the idea. Well, I was thinking really more of the bigger tunnel, and then you go through all the options there. I mean, run at Z pole and run at whatever 2W threshold, and run at the Higgs Z threshold. So yeah, I had not realized that you're talking about one or the other, right? That is just do the Z pole or the Higgs factory. So then, yeah, I'm not sure kind of who wins in some sense. Yeah.
It doesn't even have to be one or the other. I would like people like you to think about it, because if one region thinks about one option and does the best it can, another region in the world could go for the other option, such as a lower energy, very high, for example, low energy linear collider that really focuses just on the Z pole with polarized beams.
Right.
Right? So you
I see.
exploit the left-right asymmetry at the Z pole, which a circular machine cannot do.
Yeah. No, I think
If
that's a
you have
good point.
left-right asymmetry and extreme precision, do you get real probing power for compositeness competitive with the Higgs? That gives us multiple options worldwide.
Yeah. No, that's a good thought. Good idea. Yeah, I mean, I had not realized maybe that there is talk about saying what we just mentioned. Maybe just keep the LHC tunnel, but run at the Z pole, right? I mean,
could be a way to start, right? Because a big tunnel is a huge enterprise in many different ways, money, politically, this way, that way.
Right. But just to make sure, sorry, it's a bit of digression, but that's like doing LEP again, right? LEP 1 again, right? I mean,
yes, but with
LEP
new
1
cavities with more RF power.
I see. Okay. So just more luminosity, basically.
Yes, suppose.
I mean, much more. Yeah. I see.
People don't talk about it as if it could be exciting, but I think you were kind of saying just now, it could be as good a probe for a particular precision as the Z Higgs is at 0.1% precision.
Right.
That's a strong statement. Useful.
Yeah, I actually, yeah, I should qualify that. Yeah, I haven't done the comparison in detail, so don't quote me on that. I was just saying that there are these various probes, right? I mean, yeah. So again, the Higgs couplings at just 1% or actually even 1% probe. So right now the Higgs couplings are more like 10%, right? I guess.
Yeah.
So I'm saying that even going down to 1%, that's I think already probing the whatever TeV multi-TeV compositeness, and of course the reason is yeah, again the Higgs directly couples to the compositeness physics, right? So even 1% would do a good job. Whereas of course with Z, already we have done 0.1%, right? I mean, so then for the Z to go better, you'll need that to go down to 0.01%.
Sure.
And of course, the reason for that is Z itself is not composite, it's elementary. So it's a little bit screened from the compositeness effects. That's why you need a lower or a better precision, right?
Exactly.
I mean,
Yes.
right? So you need to measure Z more precisely, but Higgs, you can afford less precision for
True.
probing the same compositeness.
Clearly, if you could just have our wish, if people were just throwing money at the field, you would build a big tunnel.
Right.
But we don't want to
I mean,
solve the field. So
yeah.
if
So of
something
course,
became a problem, you would
uh,
want a backup option.
right. I mean, the other point is, of course, the Z-pole measurements are, of course, as you know, probing these electroweak parameters S and T, right? But that can probe composite Higgs, but it can probe other physics as well, right? Heavy physics. So maybe that's good, because then you might say the Z-pole factory is probing, you know, any new physics contributing, heavy new physics contributing to electroweak parameters. Right? But won't tell you that it is composite Higgs and so on. Whereas, of course, if you measure deviation in the Higgs couplings, of course, that is probing Higgs compositeness. So that gives you evidence for this idea of Higgs compositeness.
Okay, yeah, I've got it.
Right?
Yes.
So it's a
yes.
different, right? I mean, so if you want
Yes.
to really probe, or if you want to really say you've discovered Higgs compositeness, then I would say, well, the Z-pole is not good enough, because it could be some other heavy new physics.
Agreed. It's more
but,
indirect than Higgs couplings directly.
right,
Yeah.
right. But again, there's a trade-off, right? That says Z-pole can measure S and T parameters from other new physics, whereas you might say the Higgs couplings are, I mean, they're measuring Higgs coupling deviation, so likely sensitive to, even there you could say it's not just composite Higgs, but other theories where Higgs couples to something, right? Higgs portals, whatever.
Sure.
So it's those kind of theories.
Got it.
That's still a broad class, but maybe not as general as S and T parameters, right?
Agreed.
Yeah. So,
Okay. Okay,
Okay,
thanks.
thank you. One last question, Kaustubh.
okay.
Is it that we necessarily need extra dimensions to make models of composite Higgs, or can one have 4D composite models?
So I think it's a challenge, of course, because of the strong dynamics involved. So I would say a fully calculable model is hard, but of course, based on, so again, these are, the idea is to have non-supersymmetric strong dynamics. I mean, as
Yes.
many of you know, probably, if you have supersymmetric strong dynamics, then there's more calculability because of course, supersymmetry, right?
Right.
So I think people have built supersymmetric models of composite Higgs, right?
No,
But
without
non-supersymmetric is,
supersymmetry, without
right?
supersymmetry.
Yeah, so it's hard. Nonetheless, of course, based on QCD as a guidance, you can try to propose models. So in fact, the original Technicolor was exactly that, right? You just literally say scale up QCD. In fact, as we know, QCD actually breaks electroweak symmetry, does give a mass to the W. The pion is eaten by the W, but of course that's a very, very small mass, right? So the idea was really scale up QCD, literally scale up. Then you actually have calculability, because you just, you know, rescale the QCD measurements, right? F pi and, you know, everything, right? Rho pi coupling and so on, right? So that's one option, but that's restrictive, because that only allows you to calculate in models which are really literally a copy of QCD, but with a higher scale.
Okay, I
But
get.
nonetheless, small deviations from that, you might get intuition from QCD and so on, right? Now, of course, there is lattice calculations as well. So as some of you may know, there, you know, on the lattice, people are studying SU3. So, you know, 3 colors, but with different flavor. I mean, right? A higher number of flavors, 10 flavors and so on. And those actually could be candidates for composite Higgs theories. Right. So that's a totally different direction. Really, but yeah, from first
Okay.
principles calculation, right?
Thank you. And so but suppose I do have extra space-time dimensions, so do they have to be space-like or could they be time-like in principle? I don't know if you
Um,
thought about it, but yeah,
I haven't
any,
really thought, but I think, yeah, having two times that gets really tricky. So,
no, that's suppose I can handle that. I have some way, I actually have total of 3 times and 3 space, and something else plays the role of time. These 3 times
yeah,
actually become time coordinates. 3 time-like
I,
coordinates, 3 space-like coordinates, and an intrinsic absolute time parameter, which is not one of these 6. In such a
yeah,
situation,
I haven't really thought about it. Yeah, I mean, for lack of a better word, I was being conservative and saying only space-like
okay,
extra dimensions.
ठीक है,
Yeah.
I agree. All
But again,
right.
I think so to really, so again, my motivation to construct these warped extra dimensional models largely was the fact that they are dual to composite Higgs, right? So
Yeah,
sometimes
but
I'm really thinking of,
there I was worried that, and so are you dependent on ADS CFT and a negative cosmological constant? The kind of worry that cosmologists raise, no?
um, yeah. So yes, I'm using ADS CFT, so it will be negative bulk
Okay,
cosmological constant. But of course, the 4D CC can still be fine-tuned
okay,
to be zero. I mean, that was the original Randall-Sundar model.
I understand. Okay, great. I guess we are touching closing time.
Okay.
And Michael, are you there? My co-organizer, Michael, right? I don't know if Michael is there. I don't hear him. So I guess it's time.
Sorry,
Oh, Michael, you're there.
I just had to come in from the other room. Yeah.
Yeah, go ahead. Do you have any remarks from your
No,
side?
just to say thank you very much indeed for a very, very clear and for me, very enlightening talk. I learned a great deal from it. And no, and very good discussion as well. Thank you.
Yeah, same from me, Kaustubh. A really heartfelt, sincere thanks because this is a new topic. We learned a lot and we go with a sort of a flavor that we can now go and read more about it.
Absolutely. Yes, yes. I really have a feeling that I can now read a book on the Higgs and learn a great deal more from it than I could have done this morning.
Okay, great.
Okay, so thank you again for inviting me, and yeah, it
Thank
was
you.
a pleasure. And yeah, feel free to ask me any questions. I guess everybody probably has my contact or email address, or they can just look me
Yeah.
up. And so yeah, so again, the references I didn't even really bother
Great.
pointing out and so on. So, but yeah, I'm happy
We
to.
can look it up. We can look up
Yes.
your page. Yeah, great. So
Thank you for getting us off to an excellent start for the second half of this year's talks, Kaustubh.
yes. So 2 weeks
Okay.
from now, 2 weeks from now, we have Zoltan Fodor, and he will talk on the muons G-2. I think another interesting talk coming up.
Yeah,
So
that also sounds great because yeah, I've been thinking about that as well because many of us have been thinking.
yeah, so maybe we hear about that from you some other time. Okay.
So just to check, the level of the talk was right? I mean, I wasn't.
Absolutely. It was perfect. Because we come from different backgrounds.
Exactly.
It
Yeah.
was perfect. The level was perfect. Very enjoyable. We could engage with you. We could ask you questions. So really fun. One of our very nice talks in this series. Very happy to
Okay.
have you with us. Yeah.
Thank you.
Once again, Kaustubh, it really was. It was immensely clear, and
the
couldn't have
recording
been
has
better
been
judged.
done. In a couple of weeks, I think the recording will be up. Once it's YouTube, I'll send you the link.
We should have it up within a week or 10 days at the most.
Yeah, great.
Okay, so thank you again, and thank you in general for organizing this series.
Thank you. So should I close the